Hello everybody. Today we talk about the BiCMOS, a mixture of analog and digital circuit. Nowadays, a lot of chip put both analog chips and digital chips together. Before, like micro control unit (MCU) has a microprocessor, 8-bit microprocessor, and analog chip outside, and connect them together on the PCB board. But nowadays, the company can afford to make their own MCU for larger quantity, and also integration level went up so much. The designer can put the analog chip, analog function, and digital function together. For example, the AD converter and DA converter and various temperature sensing circuit. The high end is like the filter for communication. The filter for communication is like 5G chip. Even it's a digital filter. The digital filter is a mixture of analog circuit and the digital circuit. So the major difference between analog circuit and digital circuit is logic design can be used for digital side. In the previous video I explained that everything comes from logic library. You put together the logics and realize the digital circuit. It's basically logic design, but analog design you have to get down to transistor level. And the problem of getting down to transistor level is you have to check the transistor characteristic of each process technology. Each fab has a different process technology, and transistor come out to be slightly different. And you have to pick the target fab and check transistor characteristic carefully and use that transistor to design the analog circuit, because analog circuit is most likely transistor level circuit design. So it's different from logic design for digital circuit. Okay, so suppose you have MCU chip and you have a AD converter and DA converter, and also like the communication serial line CAN or any other type of serial drivers, the analog, and also you have MCU CPU chip. And that goes to memory or I/O or whatever, just regular MCU. On the chip, what is important is you never share the ground and the VCC line. Suppose you have a VCC line, you separate VCC for digital side and the ground, and analog and the ground. Well, then number of VCC and ground pins increase from the chip. So for example, this has 6 and this has 6 and this has say 10 and 10 pins. A lot of pins. The other pins are like memory bus, address bus, data bus, and stuff. The read-write control. What you do is you connect them outside of the chip, because outside of chip you can have decoupling capacitor. Okay, so these VCCs, if it's the same 5 volt you design, sometimes an analog requires 12 volt, depending on what you do. You always bring it out and connect together with this. And what this decoupling capacitor does is, digital circuit is basically very noisy, it's spiky, and the VCC is fluctuating like this, sometimes spike like that. Why it happen? Because you are switching current, and this is like a current on off. So bunch of switch, when they synchronize, it's quite a current become on and off, and VCC has some noise signal. This kind of small noise, some analog circuit can easily get on the analog circuit. Sometimes it's amplified and screw up entire operation. So you make sure that all the noise is decoupled here by outside the capacitor, and only DC component is going to be common on both sides, and any noise is going to short out here. Okay, and this is very important in the layout, analog circuit and digital circuit. And actually, PCB designer know this, because if they have a microprocessor and has analog chip outside, they do not connect together and provide the power unless you have this decoupling capacitors between. So the noise from digital never get onto analog side. Okay, the PCBs, they do that, and you have to do the same thing in the analog digital mixture chip. Okay, so in the analog circuit, it's basic circuit in the analog is like important thing is voltage reference. The voltage reference is like fixed stable voltage generated internally, and like a AD converter, it's used to compare with analog signal and digitize it. Another one is current mirror. The current mirror is like suppose you have a stable the CMOS or bipolar, same way. Whatever the current, you have a stable constant current is going to be reflected here. It's a mirror. Okay, the bipolar, actually it's prefer to have some small resistor here. I tell you the reason later. And whatever the current goes in here, constant current is going to be here, and it can be current source. When you have stable current sink here, current sink, this one sink, then this gonna provide a current sink, and by scaling the device, like this one, say 2 times bigger than this, you can have a 2A. Okay. And for accurate analog circuit, sometimes you put the resistor here, because the reason is, even you make a 2 transistor identical, there is a slight characteristic difference by process, this and this, and this small delta V BE cause large current difference. Okay, so this is kind of the so-called variability of transistor, how well the process controlled. You make a 2 transistor next to each other, usually it's pretty much same characteristic, but it's a slight difference cause large current difference. So this current mirror, this had to be careful. And also if you're not much experience in this analog circuit design, you have to also pay attention to this. The CMOS and bipolar basically same, right? Bipolar, this is exponential curve. CMOS, it's a square y equal x square curve, and you have this constant current when it's reached to saturation point. So even CV, this is BCE, this is bipolar, this CMOS is a B drain source, right? And this current is a I drain or IE or IC. It's going to stay constant even this voltage change, and this is the basic of nonlinearity we use for analog circuit. And this one is, it's really actually constant. It's not, it's slightly increased actually. So what is the problem? Well, the problem is, even you have a current mirror, you're talking about accuracy here. It's some analog circuit, you don't have to worry too much accuracy, but this I depend on this bolt and this bolt. So suppose this has a current source, there's some circuit providing a current, and this one go all the way up, say close to 4 volt, this one only 2 volt. So there will be a difference here and here, this much difference. Okay, so in this case, what you do normally, you put one intermediate transistor here and adjust this VCE voltage close to this guy, so you get pretty much same current, accurate current mirroring. So this kind of details of making a current mirror is important. Now, how do you make a current source? Well, for the CMOS, you can have some constant voltage reference, right? So that's going to produce the constant current. Then how do you make this one? This can be made by constant current sink, right? Because this is going to be Ri drop. Then how do you make this current sink? Well, it's going to go around. Which one you make first? It's all depend on the situation. Okay. Now, there is a easy way to make a V reference. It's using a Zener diode. And Zener diode has made for various voltage, like 2 volt or 3 volt or whatever. And this is 2 volt Zener diode. Once you reach to this voltage, reverse voltage, then no matter how much you throw the current, it's always 2 volt. So if you have this resistor R and VCC and the ground, this voltage stay in 2 volt. Even this guy change plus minus 10%, right? But again, the problem is Zener diode. When you make a Zener diode on the chip, there is a variability issues. Some come out to be 2.05 volt, some come out to be 1.98 volt. You have always this kind of variability issue. So how to control is the very important issue, and that was my the thesis contents. The utilizing the positive correlation, negative correlation relationship to narrow down this kind of issues. But the bipolar, there is a famous circuit. It's called band gap reference. How do you make a band gap reference? This voltage, you generate reference voltage independent with VCC variation and even temperature variation. And all the device we talk about so far is if temperature change, all the operating points shift. And in order to make a very solid V reference against the VCC plus minus 10% or 5%, whichever, and temperature range, the 0 to say 80 degree. How do you make this one? There is a very good circuit that makes. This is called band gap reference. It's used many times in the analog circuit. Basically, you have current coming down, and it's divided into 2. And the current is divided into sorry, two part, and this has the R3, and this has R2, and this is used for feedback. Again, this is the I is divided into I1 and I2. The trick is here, this voltage is a VVE, is same as this, but if you scale up this transistor, VVE is slightly smaller, and that divided by this determine the current here, I2. And this voltage is adjusted to be just same level as this one, okay? and this is a VVE3. Okay, so when you make this kind of circuit, this is gonna be very stable V reference. Okay, so V reference equals VVE3 plus VR2, right? This voltage and VVE3, this one and this one. Okay, and this voltage is this plus this, right? So VVE3 plus R2 R3 and delta VVE. Delta VVE is amplified, this small voltage amplified, plus IV3 R2. Now from here, V reference voltage is going to be VVE3 roughly, because KT over Q, J1 and J2. And J1 is this current, and this J1 current density. This current density is current is I2, and divided by the scale up size transistor is going to be J2. So J2 is smaller than J1 here. Okay, so, and this is very small, ignored. So this become pretty much independent from VCC, and we can make this even independent from temperature. How we do it? The Vref derivative 0, we set this. Okay, so VVE3 round T dt equals minus R2 R3 KQ J1 J2. Now this can be R2 and R1 instead of. So we know when temperature goes up, VVE becomes small, so it's negative. So by adjusting this R2 and R1, R3, these are constant, we make this register value pretty close to this VVE3T. Is typical VVE3 equals I0 constant VB KT. So no, this is I. I'm sorry. Hold on. Let me write it down correct. Usually the current is exponent VBE KT. Alright? So it's not Q, this is VBE. So we know this is going to be negative value. So it's possible to make a R2, R3 and R1 such a value close to this guy. the V reference derivative of temperature becomes 0. So it's going to be very nice V reference, which is independent from voltage, power supply voltage variation and the temperature variation. Okay, so it's just introduce you there is such a circuit existing to create internally on the chip the V reference. And once you have a V reference, I think it's about 1.3 volt roughly, depend on process. Once you have a constant voltage 1.3 volt, start from there, you can create current sink. If you have a current sink, you can have current source and voltage reference. Once you have this current sink, you can have a voltage reference at a higher voltage other than this one. So from here you can generate all kind of circuit component necessary for analog design. Okay, so we don't get into AD converter and DA converter here. That's gonna be another video, but so you know at least there is a way to create very good voltage reference which is very stable against the power supply voltage variations and temperature. And using this kind of voltage reference, you can create the stable current sink, current source, and higher voltage at any voltage reference you need. Okay. Well, Zener diode's accuracy is good enough for your design, then you can use Zener diode. It's much easier, but you can go accurate. It's sometimes analog circuit has to be very accurate, and accuracy costs a lot of circuit. So that's all for today. I hope you like this video, and if you like, please subscribe and put any comment down there. See you next one.